So hello everyone, good morning, welcome to the second day of the Nextflow Summit. We're going to start now with our first speaker, Bouffler from AWS. Welcome, Brendan.
Thank you. Hey everybody, welcome back. Now these spotlights are so bright that I can't see any faces out there, so it's going to feel like I'm speaking to an abyss. Anyway, that also means that you can quietly fall asleep if I'm too boring. Now, I'm going to break, that's coming up, good. I'm going to break up this talk into a few different parts, and I'm going to sacrifice some of these if we don't have enough time to get all of them in. We'll sacrifice some of the nerd bit in the middle. But the first part of it, I want to butter you up and make you feel awesome. Then I want to sort of apply some pressure to remind you that there's a sense of urgency. And we'll talk about the how and then I want to get to a call to action because there's a project that I want to get moving along a little faster that we've, a few of us in the community have started. I want to call a few of you in to ask for some favors, and we'll see where we get to. Anyway, so let's first talk about the why. So all of you people assembled here, and presumably online as well, you are very important to us. And when I say us, I mean all of the people in this photograph here. If you look very, very closely, there's about 8 billion of us. Pretty much, this is in a way, this is a recap of something I spoke about last year. It takes decades to create a new scientist, right? It's a very long process. You have to get kids enthusiastic about knowledge. You have to find kids that keep asking why. And I think we've got this entire room as assembled of a group of people that probably were those annoying kids that just kept asking why. And we need to take those kids, we need to get them enthusiastic about knowledge, we need to get them enthusiastic about science, we need to teach them lots of stuff. It takes a long time. So their population is going to start shrinking, and in particular, you can see as this bulge here starts to retire, they're going to have way more retirees than they are going to have workers in their economy. That's going to become really significant because those old buggers, and I'll eventually be joining them not too far away, even though I know I only look 29. But once we all start to retire and we age out of the workforce, we need people to take care of us. It's increasingly the case that we're going to need people to take care of us if we're not healthy. And that's where all of you come in, and it's why you're so important, because we've got a short runway to actually find a lot of cures to a lot of diseases and a lot of lifestyle issues that we've created for ourselves. And we've got to find solutions to those rather quickly. Otherwise, this bulge as it comes through and hits retirement age, and we all start to sit around in nursing homes, we're going to become a really major burden on the next generation below us. And there are not going to be enough of those people in the next generation below us to wipe our bottoms and do all those things, the really undignified things that happen, right? So keep this in mind. So this should be engendering a sense of urgency. We've never had a more, quite literally, based on the demography and based on these numbers, we've never had such an extreme need to get all of the scientific community, particularly the scientific community working in healthcare and working in life sciences research, to be the most productive you can possibly be. And so, in a way, my call to action here, at this point, is go and position yourself to be in the place where you can have the most impact. If that means switching jobs, go do it. You need to position yourselves where you can have the most impact on healthcare and life sciences outcomes that your work is contributing to. Wake up every morning and think about how you can have greater impact and really measurable impact. So anyway, so that's sort of hopefully sort of a sense of urgency that comes from that. So the point is we all care. And different countries will care a little more than others. Now, the summary of the summary of the summary. You're all weird and rare. Cores are cheaper than you. Apart from Phil and his family, cores are also more abundant. We need you to be more productive. There's a very short runway, 10 years, maybe 15 years before us Gen X start to become, really quite a big burden. So we have to solve some really big problems fairly soon. So we need to get busy, and therefore everybody cares. So there's those 8 billion people in that photograph I showed a minute ago. We've all got something at stake in seeing all of you doing what you do, but doing it a little bit incrementally better every day. So the reason I'm here at this event talking about this is because I genuinely think that this community has switched up research in this space by a huge notch. This is a lever for increasing the efficiency of scientists, building on the shoulders of others, and occasionally reinventing wheels, but to a great degree assembling things out of the parts available and then quickly moving on to bigger and better things. And I think it's been the hallmark of this community since its inception, and I've been watching this for some time. So anyway, we're going okay. We'll get a little bit of time in for some of the nerd talk. I better, do the things that pay the bills. Now, I work in HPC engineering, so really my job is to, my job and my organization's job, we are all about trying to figure out how we can make HPC simpler and get the infrastructure simpler so that you guys can run these big workloads that you run very quickly on demand and without too much fuss. We also sort of, our approach is that we don't think that we should have people with PhDs building racking and stacking machines in data centers. The specialists in our company who work on data centers have forklift driver certificates, not PhDs. The PhDs are in an office somewhere writing software that manages all of that. And, again, it's a sort of immiscible layers. Now, we talk often about this thing called infrastructure as code. And sort of, by way of context, I just want to give you a few insights to a few of the things that we've done this year that I think are sort of having a measurable impact on trying to improve this sort of, delivering an efficiency dividend so that all of you can benefit. Now, so we talk about infrastructure as code quite a lot. The cool thing about infrastructure as code is that you write down the specifications of what you want, and this thing, the cloud formation system in the cloud goes out and builds it for you, right? And so the whole idea there is that the end of it, the manageable asset that you get out of it is the recipe. So just to highlight that, it's the recipe that becomes the manageable asset. It becomes the thing you worry about, not the cluster. The cluster is really a throwaway thing. It's an ephemeral thing. You build a cluster, you get it to do a thing for a period of time. When you're done with it, you dispense with it, but you keep the recipe around in case you want to do it again. And that, do it again maybe tomorrow, maybe next week. But you get reproducible, fairly solid results all the time. Now, one of the things that we've done this year to that end is we've created this thing called the recipe library, the HPC recipe library. It's a repo on GitHub, maintained by a bunch of folks on my team. And what it's all about is actually trying to put some big building blocks in there so that we can get folks being able to build infrastructure in the cloud rather quickly without having to do all of the learning required to understand what all of those things are. And this is meant to be just a fast-track onboarding experience for people who are building workloads in the cloud and getting HPC done. HPC is hard, it's fiddly, there's a lot of moving parts, there's an incredible amount of interconnections that need to be brought together, right? So this recipe library is probably one of the more interesting things that we've done this year, which is really moving the needle in that efficiency goal. So what it does, it's built up of CloudFormation templates, if that means anything to you, CloudFormation templates and CDK scripts, and they're designed to work together so that you can take these big building blocks out of the recipe library and assemble them together, and they're designed to work together. You can have a large networking environment, a big storage environment, file caches, clusters, all of those things, and you can get it all pretty quickly. There's a lot of one-click launchers in there as well, which is basically just a super recipe built up of lots of little recipes. And what those are good for is you can take those, steal them, modify them to your heart's content, and make them your own. And then you've got a one-click thing, which becomes your one-click thing. And if you need to spin up that one-click thing in a different environment, if you're working with a collaborator and they need to copy the environment to work on, you can just hand them over those scripts. Again, it's the scripts that are the manageable asset, not the infrastructure itself. Anyway, so I think this is one of the things that my team has done this year that we've been working on, that we're very happy about, because I think it's going to have sort of like a good impact on this. Now, storage and moving data, and I heard a lot of people talking about this, in the last 24 to 48 hours. Storage and managing data in and out of the cloud is actually kind of complicated. We systematized or servicized Lustre a couple of years ago. We have this thing called Amazon FSx for Lustre. You can spin up a large parallel file system very quickly in a few minutes and have your own Lustre file system. Now, when I was last a hardware guy building HPC clusters, building supercomputers, I guess I stopped doing that about 10 years ago, building physical supercomputers when I moved to Amazon. Building a Lustre file system took 3 to 4 months. It was a big deal, and it was also a big pain in the ass when it stopped working. So the fact that we can do that with a click of a mouse is actually pretty cool. So we've systematized that. This has been a cool thing. Now, this year we came up with this, we sort of came up with another iteration of this, another kind of approach to this, called this thing called file cache. And what file cache is actually taking a Lustre file system and using it as a front to things that are behind it, like an S3 bucket or an NFS filer. And those S3 buckets or NFS filers, they could be local, they could actually be far, far away, in another region, in your own offices, in your own buildings, in your data center, in someone else's data center, right? But you've got a Lustre layer sitting in front, which suddenly makes the entire thing very POSIXy and extremely fast. Really good for lifting a public data set out of an S3 bucket and turning it into something that you can do an insane number of IOPS on. Hundreds of gigabytes a second, lots of IOPS, and so forth. So we are working on this, and you can unify different things. You can, one of the cool use cases is to take something that's a bit of S3 over there, a bit of NFS over there, and maybe a bit of other local stuff nearby, and make it look like it's a single file system. There's some cool aspects of that, and I encourage you to have a play. But more to the point, reach out if this is not doing what you need it to do. As with all of this stuff, you guys know how to find me. I'm on the Nextflow Slack. If there's feedback that you want to give to us to let us know that something that we've built is not behaving the way you need it to behave to get that efficiency dividend, we need to know. And so just drop me a Slack, get back to me. I'll make sure that that information lands in the hands of the engineers and the product managers that are designing and building it. Now, I think batch is a wonderful thing. I'll say that. Batch is actually probably the service that most of you are using. We did a lot of work this year on the fair share scheduling in batch. So if you're using an AWS batch environment and you're sharing it amongst a bunch of different users, fair share scheduling may actually be something that you really want to look at doing in order to reduce the friction and tension between you and your neighbors that are sharing the same thing, the same resources. So have a look at that. But I kind of want to quickly get on to this next topic. So last year when I was here, we announced this, which was the biocontainers mirror in ECR public, so the Elastic Container Registry. If you're not using this and you're using AWS, you really should. If you're not using this and you're using some other system or environment, you probably should be thinking about using this as well. The cool thing about this ECR public mirror of biocontainers, it's fast, really fast. It's really fast if you're inside AWS, that kind of makes sense. But we actually fronted the whole thing with our CDN, a thing called CloudFront. And what that means is that if you're in, I don't know, Melbourne, pulling a container, the first time it'll take a little while, but that's more or less the same experience you have, say, using the biocontainers on key.io right now. But the second time you get it, it's going to be super fast because it's going to be in the edge cache very close to you in your city. It doesn't matter whether you're in Melbourne or Madrid or Milan. right? Or Milwaukee. There you go. I found another M in another part of the world. So if you're not using this thing, give it a try. It's literally a single line change in your configuration file, and you can get access to this. This is going to be much, much faster and could actually speed up some of your pipelines. But while we were working on that, one of the questions we've been asked by a lot of customers is, can we have an ARM mirror of biocontainers, so that it's not just x86 that everybody's driven to use, it's ARM. And the reason for that, and it makes a whole lot of sense, ARM is actually really cheap. Let me see, I've got a slide there. So the thing on the right-hand side is the HPC instance we launched mid this year, made up of the thing that we call the Graviton, the AWS Graviton. That's our ARM-based processor. Slightly souped up version of the architecture in your Apple M1 or M2 is actually majorly souped up. It's got really pretty incredible memory bandwidth. It's a groovy little CPU. It's amazing. Goes toe-to-toe with its x86 cousins in terms of performance, but it's about 40–50% cheaper. Carbon footprint is 40 to 50% better in terms of, flops per watt, if you think about it from that point of view, or flops per ton of carbon. So it's a pretty amazing processor, and a lot of folks are moving to it. Now, so the question that we got asked, more or less as I got off the stage last year, people were asking me about an ARM version of it. And so we really do want to get that happening. Now, there's a bunch of different groups in the community who've been doing a bit of work to port much of what goes on in Bioconda into an ARM binary universe. But there's a group that we work with on the sort of the traditional HPC side of the house, on the supercomputing side, right? So Department of Energy, national labs in the US, where we do a lot of work with those folks, Lawrence Livermore and some of their friends. They've come up with a tool called SPAC. Now, this is sort of a fairly normal dependency tree for a fairly simple HPC application called Tinker. It's a molecular modeling tool. It's considered to be a mini app, so it's not considered to be something that's that complicated. But you look at the dependency matrix here, and it's just bonkers. Anything changes in there, and it's just chaos in the build environment. So these nice folks in SPAC, the open source community called SPAC, solve this, and the SPAC tool is that first 5 characters of that command there. Boy, is that doing a lot of work. SPAC is it's an HPC package manager that understands all that complexity, and it just goes and finds all of the source bundles for you. SPAC's built on recipes, and it can pull a recipe out of its recipe set, pull all of the dependencies in, build them, get the thing working, and in, I don't know, maybe 30 minutes you've got BWA ready to actually run. And the whole thing's compiled and working really well. Then we kind of pushed a little bit further forward and worked with the SPAC team, and we said to them, why couldn't we have like a giant build cache? Why couldn't we have a binary build cache? When somebody builds one of these things, spends the CPU cycles to actually compile all these things into binaries, why can't we have those binaries be available? And they said, that's actually an ingenious idea. So we all got together, and AWS actually funded most of the compute that runs behind this. My team, we sat and looked at this and thought, this is one of these places where we can just move the needle really quickly. And if it means that we no longer have scientists sitting around waiting for 2 to 3 or 4 days, pulling all of the dependencies together and compiling them, this is just a major win. So we put a tremendous amount of compute behind this, and what's come out of it is the SPAC binary cache. And for a bunch of different architectures and a bunch of different environments, including an ARM-based environment, so ARM64 binaries, there is a giant binary cache of applications. And the convergence between the x86 cache and the ARM cache is actually, they are converging over time, and we're starting to see, pretty good outcomes. But necessarily, what is hard is unit testing and optimizing. So building something is partly a barrier to many of these codes, and there's just an awful lot of x86 assumptions built into people's makefiles and build scripts and so forth. There's a lot of x86 assumptions, there's a lot of compiler assumptions. Then, of course, at the other extreme, there's, can we actually get everything not just building and running, but building and running fast, right? Because ultimately, fast is the goal. This is high performance computing. So here's what I want to kick off today. So we've been doing a lot of work with Marco, who's a new member of the Sakera team, but has been a Nextflow member for some time, Nextflow community member for some time. He sort of lives in both universes of the Bioconda world and the SPAC world because of the job that he used to have working at a supercomputer center. And Marco's done an awful lot of work to sort of take some of the ideas from SPAC and see if they can work over here. But in order to get a large-scale effort going and to bring it to completion, and really to get 99% of all of the, of all of biocontainers to be, executing happily on ARM64 CPUs, whether they're, Gravitons or some others, or the ones on your laptop. In order to get that to happen, we need a few things. We need to crowdsource some of the effort. So we're going to, in the first quarter of next year, we're aiming to have, my team we're gonna try and stand up this is a crazy idea, it's called a build jamboree. We're gonna get an enormous number of people from around the world, and we're gonna get together over a weekend in a lot of cities, probably eat a lot of pizza and drink a lot of Red Bull, and we're gonna see if we can actually get an awful lot of these recipes working on both sides of the house so they just build. And we think that'll be a good, be a useful community effort. But we also need unit tests. And I think this community, particularly when it comes to codes in Bioconda, you guys have got all of the unit tests already, I suspect. They're in your pipelines. And so I do want to see if we can solve that problem. Because once we've got unit tests, we've got an awful lot of clever people over at ARM who are willing to put some effort in ARM and in AWS and in other companies as well and other places that are willing to put the effort in to see if we can optimize this stuff to make it run faster on ARM. So anyway, so that is my ask to you. Don't be shy. You know how to find me on Slack. Most of the, some of my teammates are there as well. And we can get some interesting conversations going. Marco is the guy in Sakera and in the Nextflow community who's really leading the charge on this. And I'd like to see if we can pull together some of the folks from around the community to see if we can all get together and clean up this particular yard and see if we can make things work much, much faster. Anyway, in the end, you all know what the goal is, right? The goal is that we've got something like a decade left to get all of you and all of the people that you support being incredibly productive, because we need you to solve some really big diseases and lifestyle issues and medical issues at an enormous scale, and the pressure is on. Anyway, thank you. I hope I didn't depress you. I hope I've kind of motivated you, but thanks for coming. And thanks for this community. And particularly kudos to this guy up the front here who's been key to starting this movement. Anyway, thanks very much.
So we're a bit tight on time, so we'll go to the next speaker. Thanks, Brandon.
No problems.